Pengliang, I'm going to turn things over to you, and thank you very much for being here with us.
Okay, thank you, Chris. Can you see my screen?
Yes, it looks great.
Okay, yeah. Okay, hi everyone. Thanks for coming. I'm Peng Liang, currently as a postdoc at Penn State, supervised by Derek Edwards and Chris Maron, and also collaborating with field researchers including TM, Prisa, Roland, and David. Today, I would like to show some artwork about empowering enhanced geothermal system by integrating the modeling and the laboratory experiments. Uh, there are huge amount of the deep geothermal resources in the world and also in the US, of course. For example, the IEA estimates that the US deep geothermal potential over than 7 terawatt at depths up to 5 kilometers. If we consider the depths up to the 10 kilometers, the deep geothermal potential is over 70 terawatt. Of course, the potential is not the same as the near-term deployment. So in terms of what we could realistic to be built, the US DOE indicates that geothermal could reach at least 90 gigawatts of electricity generating capacity by the 2015, with continuous technology advances. So what does the 90 gigawatt actually mean? If we're using EIA's 2024 average residential electricity use about 863 kilowatt hour per household per month, the 90 gigawatt firm continuously power corresponding to the electricity for roughly 70 million houses on average. So building on the resources picture from the previous slides, the key point is that the most of the geothermal energy is stored in the hot and dry and low permeability crystalline rock, often referred to as hot dry rock (HDR), typically at the depth of roughly 3 to 10 kilometers, where temperature accumulates over than 150 degrees. The change is straightforward. The HDR contains plenty of the heat, but not enough for the permeability to circulate the fluids at commercial useful rates. So that's exactly why the concept of enhanced geothermal (EGS) were introduced. What's the EGS? The EGS actually is to engineer a connective fracture network to enable the efficient circulation and economically viable heat extraction. In practice, the reservoir creation can involve the hydraulic fracturing, shear stimulation, and also sometimes chemical stimulation, and also some other approaches. So the EGS actually is not a new idea. It dates back to 1970s, starting with the pioneering the Fanning Hill project near the Los Alamos. Since then, more than 70 EGS field projects have been launched worldwide. However, only a few have processed to sustain commercial electricity generation. The EGS have been a story of the big promise and also a lot of lessons actually. If we look at all those projects, many have failed, paused, or have been permanently shut down. The Polex summarized several changes. But today's talk, I would like to focus on two of them that continually consistent control whether the EGS project can be both safe and economically viable. The first one is induced seismicity, which becomes a major constraint on the safe operation and public acceptance. The second one is insufficient connectivity, means the fracture network doesn't form a durable and well-connected flow path between the injection and production well, so we cannot sustain the circulation rate needed for reliable heat extraction. So the first change in induced seismicity is a true game stopper in many EGS projects. There are a couple of mechanisms that could induce seismicity. The most direct one is the pore pressure increase, which reduces the effective normal stress on the pre-existing fractures and fault. And the reduction lowers the frictional resistance and can bring the fault close to failure, especially if they're already near the critical stress state. In addition to the pore pressure diffusion, the pore-elastic stressing can also trigger seismicity, and the injection causes the rock volume to expand and deform, producing the stress changes that could be transmitted away from the well. And the pore-elastic stress transfer could permit the failure outside the region of the significant pressure increase, and also some other mechanism to induce seismicity about seismic slip and also the thermal stress. So one of the notable examples for the induced seismicity is the 2017 the Pohon EGS project, which caused a magnitude of earthquake 5.4. The key explanation of this earthquake is that the operations like the perturbated fault that are already close to failure, and in particular, the PX2, the well already have intersected and hydraulically connected to a fault zone. With the repeated injections, the pore pressure and the stress conditions involved until the system transmission to the runaway rupture of that fault. So if you look at the injection seismicity history in this figure, there is a pattern that shows up repeatedly actually. When the injection rate ramps up, the seismicity rate corresponds to almost immediately, and this feedback ultimately results in the reactivation of the larger fault system. Another major barrier is to make the EGS technologically and economically viable. By achieving the sufficient hydraulic connectivity between the injection and production wells. From the techno-economic perspective, some research indicates that an EGS production well needs to sustain the circulation rate on the order of the 80 kilograms per second to reach the competitive power output and the cost. In practice, this is hard, honestly. If the stimulation creates a fracture network in the wrong direction and poorly connected between the two wells, and we cannot get the target flow rate. And even sometimes, if we do connect between two wells, but the flow may be only concentrated into a single preferential path, which will cause nearly thermal breakthrough, and the produced fluid could cool too quickly to become short circuit, and instead of sweeping the large heat exchange area. Currently, a promising approach is to use the horizontal well multi-stage hydraulic fracturing design from the oil gas department company to create a large and well-connected flow path. A good example is for NG, the recent field demonstrations in their Project Red pilot. A 30-day circulation test achieved about 63 kilograms per second at high temperature, and more recently, the Cap station, they reported a maximum flow rate of over 100 kilograms per second for a month test by using such design. Conceptually, this design is straightforward. So the cold water is injected from the injection well, allowing the flow to extract the heat, primarily force the convection in the fractures with conductive heat recharge from the surrounding rocks into those flow paths. The heated flow then returns to the surface through the production well. I call this design as the Foley brain design because the hydraulic fracture directly connects the injection and production well. This sorry. So this Foley bridging fracture design can deliver a strong and stable circulation rate. It also introduces a key trade-off. If the flow rate is very high, while the effective fracture length and
you came here, right? Is it here microphone?
Yeah. Can you hear me? Hello? Yeah. So if the flow rate is very high, and while the effective fracture length and surface area is limited, the water might not be heated up enough. In this case, we have the risk of thermal circulating. And more broadly, once the convection effectively transports the heat within the fracture network, the bottlenecks becomes the conductive heat recharge from the surrounding rock into the flowing pathways. So that means the effective heat traction volume is constrained by how far the injected cold front penetrates to the stimulated reservoir volume. So that motivates the question of can we keep the higher circulation bandwidth but also delay the thermal breakthrough? To address that, we propose a partial bridging fracture design. As shown in this animation, we stimulated the fractures from the both injection and production well, and the fractures grew from the injection well but do not intersect with the production well. So the fractures growing from the production well do not intersect with the injection well. So this design could prevent the water flow directly from the injection well to production well. Instead, the water in the injection fractures must enter and flow through the SRV and then exit in the fractures that's connected with the production well. So compared with the follow bridging, the EGS design, this partial bridging EGS design could delay the thermal breakthrough and promote the greater cumulative heat extraction by forcing the fluid to sweep the larger effective reservoir volume. To test the partial bridging concepts, I built a set of coupled thermal-hydromechanical THM models to quantify how this design performs during the long-term heat extraction. We know the thermal production in the EGS is a coupled program. We have the hydraulic process, where the pressure diffusion and fluid flow through the fracture matrix system, and also the thermal transport process, where the heat transported by the advection in the flowing fluid, and also conduction in the surrounding rock. And the rock mechanic process, where the thermoelastic effect and the poroelastic stress are showing. The thermoelastic stress is driven by the cooling, and the poroelastic stress driven by the pore pressure changes. Because the fracture is fundamentally two rock surfaces in contact, we model the fracture using a contact mechanics model that allows them to open and close dynamically. In the animation, you can see there's a localized line cooling source along the part of the fractures that could induce the thermoelastic contraction of the cooling rock, and that contraction could reduce the normal stress locally and promote the fracture opening. In terms of geometry, the model includes 4 horizontal fractures, 2 connected with the injection well and 2 connected with the production well. Here, we compare the production water temperature from the production well for partially and fully bridging EGS design. From the figure, we can see the partial bridging model could produce water with a longer term stabilized temperature and a reduced cooling rate compared to fully bridging design. What we also find is that the partial bridging design could also produce a large failure volume. That could indicate the stronger secondary stimulation compared to the fully bridging design. This is because the partial bridging design forces the cold water flow from the reservoir and generates the broader thermal and pressure perturbations, and therefore causing a larger region towards the shear failure. The secondary stimulation is quantified using the reservoir volume concept as the portion of the reservoir where the involving stress state meets the shear failure criteria. Because the partial bridging design drives the larger secondary stimulation, it also tends to increase injectivity, especially once we allow the stress-dependent permeability enhancement within the stimulated reservoir volume. As shown in this figure, the SRV permeability is allowed to evolve dynamically with the stress state, and the effective SRV permeability increase with increased injectivity. And we could also circulate the more fluid flow efficiently with more heat extraction. However, there is an important trade-off. The SRV permeability enhancement could cause the induced seismicity. For example, we estimate a relative seismicity rate using a proxy based on the volume-weighted change in the excess shear stress across SRV. Then we compare the seismicity evolution over 20 years production for 2 cases. One is constant SRV permeability model, another one is a stress-dependent SRV permeability model. As shown in this figure, in the right figure, the key result is the permeability enhancement increases the induced seismicity rate, especially in the early production period. This is because the largest temperature gap between the injection temperature and the reservoir temperature in the early production period which result in significant thermal contraction and extensive shear rate changes. Then we further analyze the driving mechanisms between the thermoelastic and the poroelastic effect on the seismicity. By comparing the models that isolate the thermoelastic effect, poroelastic effect, and their combined thermoporoelastic response, we found that the thermoelastic stressing is dominant control on the seismicity rate within the SRV. By contrast, the poroelastic effect plays a stabilizing role. It tends to stabilize and delay the small stress changes that could promote the failure. We could see in the figure A, the thermoelastic model have the thermoporoelastic model have smaller seismicity rate compared to the thermoelastic only model. The physical reason is that the poroelastic coupling allows the pore pressure diffusion and associated volumetric deformation to redistribute the stress in a way that partially offsets the thermoelastic loading. So far, I have shown some how the induced seismicity could evolve during the long-term production under the coupled thermal poroelastic effect. And stepping back, we also know that during a hydraulic and shear simulation, the induced seismicity essentially cannot be avoided. So what can we do is to understand, anticipate, and also manage it. So in fact, in the shear operations, microscopic MEQs are routinely used as a practical diagnostic because it could help the map where the structures are activating and how the stimulated reservoir volume growing. This also raises a natural question for the EGS. Can the MEQs inform the stimulation state and performance of the EGS reservoir? Things like if they could inform the connectivity, permeability creation, and ultimately the heat extraction performance. Some researchers already starting to thinking about this a long time ago, actually. ShapeRoll shows that the special chemical migration of the microscopic during the simulation can approximate a pressure triggering diffusion front because the pressure perturbations and activates the critically stressed structures and small faults. Once the local threshold value is reached, fitting the MEQ migration, we could also get the hydraulic diffusivity, which can be converted to an effective permeability. Later, Rifault and Dempsey proposed a mapping permeability structure during the Habanero well simulation in Australia. By using the hypocenter density of the microscopic as a proxy of the pore pressure, and they found that for the Habanero EGS well 1 simulation, the MEQ cloud can be bigger than the stimulated reservoir volume as shown in this animation. This actually reasonable because the microscopic map where the fracture slips. The fluid permeability depends on the connectivity, aperture evolution, and whether the slip occurred on the hydraulically connected fractures. Another interesting study is by Chen and published recently in the Geophysics. They used the special temporal migration of the microscopic to represent the regions with different hydraulic diffusivity and then convert it into that as a first order estimated permeability. And using those seismicity constrained properties as input, they can run the forward tracer transport simulations and calibrate the model against the observed tracer breakthrough data. The key result is that our permeability distribution constrained by the seismicity provides the better match of the tracer test data than a more uniform or uncontained permeability model. So those studies give some clues of the microscopic may be linked to permeability creation, but the hard part is making that the link quantitative and predictive. So we know the microearthquake is fundamentally a noisy and spatial temporal data. The events sometimes are unevenly detected at location, carry uncertainty, and the relationship of the flow is indirect. So that's where I think the machine learning and deep learning can help, as it has strength in extracting hidden structures from the pattern, and hidden structures and patterns, and from the large and noisy data set. So the question we can ask is, can we use the MQ's observation to predict the permeability evolution during the simulation? To do that, we need a dataset with simultaneously and high quality measurement of both seismicity and permeability. In this study, we got the data from the EGS Collab Experiments 1 conducted at the Sanford Underground Research Facility at about 100 kilometer depth. The experiments are conducted in the crystalline rock at a decameter scale with dense monitoring and controlled stimulation conditions. So in this study, we combine the hydraulic record with the MEQ catalog from 3 continuous simulation episodes, the episode 3, episode 4, and episode 5, and using a deep learning framework to learn how the MEQ is related to permeability change. The workflow has 2 parts. The first part is to estimate the permeability evolution from the hydraulics, and then extract the MEQ features to predict that evolution. First, from the raw injection data, we calculated the injectivity. During the simulation, the increase in the injectivity as a practical indicator of the permeability enhancement. Next, we fit the MEQ space-time evolution using the Shapiro diffusion model, which could be used to get the MEQ migration radius away from the injection point through time. Then, based on the assumed flow geometry constrained by the MEQ distributed geometry, we could convert the injectivity into an equivalent permeability. On the MEQ data side, we extract 2 simple but physically meaningful features from the MEQ catalogs: the cumulative seismic moment and the seismic rates that are calculated in a moving 1 minute time window. Finally, because we care about the change rather than absolute values, the predict target is a normalized permeability change expressed as a permeability ratio with initial permeability in the log space. After extracting the 2 MEQ features and defining the permeability change target, we trained a bi-LSTM model to predict the permeability changes then directly using those 2 extracted seismicity features. We used episode 3 for training, episode 4 for validation, and episode 5 as fully unseen test data, so the test case could represent an independent simulation episode. Because the EP4 and EP5, episode 4 and episode 5 can differ in a scale from the EP3, so we apply the sample-by-sample normalization to validation and test input to reduce the out of the distribution effect, and we also incorporate modified loss functions that could encourage the predicted permeability to be more monotonically increased during the simulation, which is consistent with the physical expectation of the progressing permeability enhancement over the injectivity episode before the peak injectivity. As a result shown here, the bi-STM module captured the permeability evolution well, not only on the validation episode, but also on the unseen test dataset, which demonstrates that the cumulative seismic moment as a feature that related to permeability change. So the bi-STM model result suggests that the seismic moment carries information about the permeability change. The next question is, what's the physical mechanism could explain that link? So here we derived a mechanistic relationship between the seismic moment and the fracture permeability, starting from the shear slip of the rough fractures. During simulation, the shear slip could produce MQs, and at the same time, it can change the permeability of the fracture because the slip on the rough surface produces shear dilation, and two fracture walls step up and cell prop, so increase the aperture. So from the shear dilation sense, the fracture aperture change can be related to shear displacement through the dilation and roughness relationship controlled by the roughness of the rock and the fracture. The fracture permeability is directly related to the aperture in the cubic law. And the seismic moment is directly related to the slip where the shear modulus, slip area, and shear displacement. Putting all those together, we combine a direct scaling between the permeability enhancement and seismic moment accumulated during the shear slip. In our final form, we found the permeability change becomes proportional to seismic moment with a coefficient that depends on the physical meaning parameters such as the shear stress drop, fracture roughness, dilation, fracture spacing, or the activity area, and the shear modulus. So the next one is we want to validate the relationship in the well-controlled lab. The experiment is conducted using a granitoid core sample from the Utah Forge project, so cut at a 30-degree angle to along its column direction prior to the experiments. The fault surface are roughened using the city granite pounders to create controlled surface roughness. And the sample is then confined between the two steel end caps connected with two fluid lines. The end caps actually have both the fluid lines and also the ultrasonic transducers assembled inside. Then that could be covered in a jacket to isolate the sample from the fluid used for the confining pressure. The sample is placed inside in a triaxial chemical co-holder. Three hydraulic pumps are used to control the axial confining upstream and downstream pressures. The pump A, pump B, and pump C. The pump A is used to add the confining pressure and axial pressure. Pump B controls the upstream pressure to drive the flow through the fault, while the pump C receives the flow from the downstream side. All the pumps are operated remotely using the LabVIEW and a displacement sensor, the LVDT, with a resolution of the 0 micrometers is connected to the axial piston and monitors throughout the temperature, the experiments. The experiment begins by setting both the axial and confining pressure to 10 megapascal using the pump A, and then when stabilized, the wall connecting the confining pressure to the pump is closed, and to maintain the constant confining pressure using the pressure release valve, the PRV. And the axial pressure is then increased to the 80% of pre-shear shear strength. Then we can keep the boundary condition as a zero load point displacement by locking the loading piston. This is showing one of the representative experiment results that conducted with zero load point displacement boundary condition. The downstream pressure was maintained at 0.5 megapascal, with the upstream pressure increased by 0.5 megapascal every 3 minutes, allowing for a new steady state flow condition achieved. So we could calculate the steady state permeability for each pressure step at the end of each pressure step, and that could be correlated to the initial shear stress, shear displacement, and relative to the shear-induced AE acoustic events. As shown in this figure, the majority of the AE events are observed to accompany the shear displacement during each pressure step, corresponding to the application of the increased upstream pressure. So to study the relationship between the permeability change and the seismic moment in each pressure step, we need to calibrate the PZT sensors by converting the AE amplitude to the seismic moment using the ball drop calibration experiments. So we calculated the incremental changes in permeability and by using the current step, the permeability minus the last pressure step permeability, and we evaluated the sand moment for each individual AE events from the absolute calibrated ball drop impairments. And then we summed them within the 4 period for each pressure step. The sum of the sand moments in each pressure step then are evaluated and plotted against the permeability change in each pressure step as shown in the figure. We can see that for the lab impairments, we generate the earthquake in the range of magnitude from -8 to -6. And for all the 5 impairments we're showing here, there is a linear relationship between the sand moment and the permeability change as shown in the double log space plot. Then we want to further test if the physical relationship we proposed between the sand moment and permeability change could be used to predict the permeability changes in the lab impairments or not. So we calculate the stress drop in each pressure step and applying the equation we derived here to calculate the permeability change using sand moment. We found that as shown in the figure, the equation we proposed could use to deterministically calculate the permeability for each of the impairments with good R squared. This is not only showing the linear relationship between sand moment and permeability in the lab scale, but also demonstrates that the deterministic capability of the relationship in calculating the permeability from the sand moment data. As the lab impairments is conducted in the centimeter scale, and we also want to see if the relationship between the sand moment and permeability change still hold across the length scales. So in the left figure, we added more data from the field. We added the EGS collapse and Utah fault impairment data. The EGS collapse stimulation impairments were conducted in the decameter scale, while the fault impairments is conducted in the sub-kilometer scale. If we try to extend the linear relationship observed from the lab to the field, we found it looked like this relationship could work for the EGS collapse data in the decameter scale length. However, the fault data is a bit away from the linear line. That might show that there is a different scaling range between sand moment and permeability across the length scale. So this mismatch of the linear relationship at larger length scales make us to reconsider the scaling relationship. In the single limited scale, the deterministic prefactor, the omega scale with sand moment with permeability change is a function of the shear modulus, roughness, stress drops, and the fracture spacing. Observe the shear modulus is decoupled from the size of the sloping fault patch. However, the roughness, effective shear stress, and the fracture spacing could be linked with to patch size. And the moment stress drop and patch radius are also linked in a penny-shaped crack sand moment calculation equation. From there, we further derived a power law scaling relationship between the permeability change and sand moment. To test the scaling relationship across scales, we use the parameter range of the stress drop, fault, roughness, and shear modulus range shown here to quantify the scaling prefactors of the lambda in the figure. And we found that observations from the laboratory shear impairments at the centimeter scale, EGS collapse at decameter scale, and the Utah fault at some kilometer scale all fall across the range of 10 to minus 3 times the maximum of the lambda to 10 to minus 1 times the maximum lambda. So, and there are no bias for the less scales. So we also conducted a regression analysis to using the power law model of the delta K equals eta times the sand moment with a power law exponent of beta on those 3 subsets of the data. We consider the 3 regression analysis. The first one is only do the regression on the all laboratory permit data. The second one is do all the field data, the EGS collapse plus the Utah fault. And the third one is the 4 data set combining the both impairments and field observations. For each of case, we evaluated the coefficient of the determination, the R squared, to evaluate the quality of the fit. For the laboratory data, the best fit model we got is the power law improvement is 0.997. That indicates a linear relationship between side moment and permeability change within the centimeter permeability scale. That could also further validate our derived linear proportional relationship previously. And when the model is fitted to the field data, the results, the best fit power law improvement is 0.5. However, this cannot incorporate the lab centimeter scale data. When we do the regression for the full data set spanning across all length scales, the best fit power law improvement is 0.787. And this model performed well across the laboratory and field data, supporting the existence of the length scale consistent power law relationship. And the fitted component of 0.77 is quite close to the theoretical derived value of the 2/3. They could also further show that the physical validity of the proposed scaling framework. So then we further want to use this derived scaling relationship to map the in situ permeability change using the side moment from the field data. This is ongoing work. We use the Gonghe EGS shared simulation data as from the well GH01, 02, and 03 to map the permeability by directly using the waveform of the from the seismic station to calculate the source radius and strike drop, and then apply the derived relationship to calculate the permeability. As shown in this animation, the permeability distribution result showing that here it will be could also further validated by using the fluid circulation and tracer flow test data. So yeah, this is a summary of the talk. We proposed partially bridging multi-stage fracture design to delay the thermal breakthrough while maintaining the higher circulation flow rate. And then we proposed permeability and seismic moment relationship by incorporating the machine learning and well-controlled lab experiments. And this framework has the potential to evaluate the simulation performance during the simulation period instead of current all the method is focused on the post-simulation period. Yeah, that's all. And we'd like to thank the support from DOE and also Utah for the funding. And thank you. And happy to answer and take any questions. Thank you.
Thanks very much, Pengliang. Yeah, I'll invite people to join me on mute. Turn your camera on if you'd like for a second. We can give Pengliang a minute to catch his breath, but yeah, lots of interesting things to think about.